Document store technology can reduce cost and increase operational throughput for 3V systems: high volume, high velocity, and high variety. In short, they were made to manage big data. They do this primarily by breaking up data management tasks in a way that's designed to support parallel processing. The image here provides the big picture. Applications, users and web servers, which make requests to any of several available master nodes, who route data management tasks to one of several data nodes. Multiple interchangeable servers allow parallelized efficiency. This slide deck explains the lower level strategies needed to make effective parallel processing a reality. To understand this material, you should already understand a few concepts. If you don't have these concepts down, go back and review the previous slides. The decision to use a NoSQL document store instead of a traditional relational database management system is complex and depends on many factors. But one thing is clear. To get value from such a system, you have to execute on several important sub-strategies. In many ways, these sub-strategies reflect a direct contradiction to many of the key ideas that guided the development of the immensely powerful and reliable relational database management systems on the market today. Strategy 1. Instead of buying a few expensive servers for a relational database cluster and then installing software with a six-figure price tag, buy many inexpensive computers and install relatively inexpensive NoSQL software. Strategy 2. Design your data structures to minimize the need for joins in your most time-sensitive operations. Strategy 3. Partition your managed data onto multiple servers to facilitate parallel processing. Strategy 4. Relax integrity and security controls that slow down processing without really mitigating any important risks. You might want to listen to that list again. We will look at these strategies in more depth in the upcoming slides. Modern computing environments achieve increased throughput by having multiple computers perform tasks in parallel. No one computer in the set could handle the massive data management load, so both the data and the processing tasks are split up across many units. From a cost and scalability perspective, this is a great idea because even relatively inexpensive computers are very fast, completing billions of instructions per second. Extremely fast computers are expensive because it costs billions of dollars to develop new, increasingly fast models. While real-world performance can depend on a number of factors, a single computer able to compute at a given rate is probably much more expensive than a collection of computers that, together, can complete the same amount of computation per second. Actually, the collection of computers is probably far cheaper. If you use a single computer system for your database, you may have to spend a lot all at once to increase its capabilities. But if you use a large number of inexpensive units that share the load, you can probably increase capacity a bit at a time by adding units as you go along. For most growing organizations, it is better to spend $10,000 for a moderate increase in power instead of $40,000 to make a big jump. Being able to incrementally expand your system is a good thing. But there also is a big downside here. When you have lots of computers, some of them are bound to break. Inexpensive models are built, well, inexpensively. That means that each inexpensive computer is more likely to break than a single expensive mainframe is, for example. In short, a database system that employs multiple servers has to be prepared for failure of individual components. While the additional performance achieved when multiple computers each handle a few tasks is pretty clear, that is really only half of the multiple computer story. The increase in hardware failures associated with employing several inexpensive computers would create a big problem if all of the computers had to be working all of the time. NoSQL systems intentionally employ redundancy so that even if one computer fails, all needed activity can still be completed. This means that both coordination and data handling functions should be configured so that operations can fail over to redundant computers in the case of a malfunction. The diagrams we are using in this presentation differentiate master and data nodes. Actually, that is a simplification. Hadoop, MongoDB, and other NoSQL technologies each include several types of servers that can play different roles in the data management process. For our purposes, we will simplify things and call a server a master node if it plays a coordinating function, and a data node if it primarily reads and writes stored data. In Hadoop, a widely used NoSQL data management platform, master nodes include job trackers and name nodes. In MongoDB, a document store, master nodes include routers, called mongos, and config servers, while shard servers manage assigned parts of actual data sets. Some coordination has to be done so that a group of master nodes can manage multiple requests. This takes communication and involves shared data that cannot be fully parallelized. For example, each task as it comes in has to be assigned to a single master node for coordination. This means that some routing master node interacts at least briefly with each incoming task and has to monitor available resources. Parallelized NoSQL systems usually designate primary servers to facilitate this kind of unavoidable coordination task. Primary server-only tasks are carefully limited to avoid creating unnecessary performance bottlenecks. Then programs monitor things in case the primary fails so that the load can be shifted to a backup server. Designing and configuring redundancy is a complicated process, but in the end, it's all about ensuring that nothing is lost when inevitable hardware failures happen. A database system is considered to be a document store because it stores data in documents instead of in rows in a table. As illustrated in previous slides, document store documents should be organized so that all the data needed to complete a task is stored in a single document. Deciding which data belong together in a document is all about understanding the task. For example, tens of thousands of customers simultaneously access their shopping carts in large online retailing environments. A document store arrangement would keep the many details, such as customer details, product details, quantities, and shipping information, for example, all together in a single document. In a document-based system, one request to the database manager would retrieve everything you need to know about a customer's shopping cart. To accomplish the same task in a relational system, you would need to integrate data from multiple lists, perhaps including a customer list, a product list, a shopping cart list, and an items in shopping cart list, and maybe even more. We refer to the process of selecting from multiple lists and integrating the results as joining. Joining creates contention as lists are shared by numerous requests. Continuing our example, if needed customer data is on one server and the product data is on another, those two servers have to work together in a join scenario. If several shopping cart updates come into a relational system at the same minute, those requests can compete for access to the underlying lists. Even when a relational system is configured to employ multiple servers, there can be contention for shared resources. Requests often have to get in a single line before they can be processed. This diagram illustrates the extra steps needed when performing data retrieval from a normalized table structure as contrasted with a hierarchical document. In the normalized design, with multiple tables, each table has to be accessed and the data have to be integrated. Although the steps to integrate the data are probably done behind the scenes in response to a simple query statement, the multiple steps may have to be done one after the other. In our example, the system would need to retrieve the customer's shopping cart ID. It would use that ID to get the items in the list. Next, it would use the retrieved item numbers to access the product list. Then it would put the data together for further processing. Queries can use indexes to find and retrieve needed data elements, Although well-configured relational systems can do this with amazing speed, all other things equal, accessing one index for one list is generally faster than accessing three indexes for three lists. So, when moving to a document store, developers refactor organizational data into a hierarchical form targeted to support the most time-critical transactions. Once an appropriate document design is in place, data is partitioned into subsets and spread out across multiple servers. Because joining has been minimized, multiple master nodes can be asking for data at the same time with little contention. The total throughput of the systems can be boosted by parallel processing. Further, performance can be boosted by adding additional processing nodes to the cluster. Careful consideration needs to be given in dividing up the data into the right subsets, or else the advantage of parallel processing may be lost. Datasets are partitioned into multiple shards to be handled by separate data nodes. For example, shopping cart documents could be divided up amongst a set of shards in order by the date and time they were updated. If it was done that way, a very large portion of the work at any one time would have to be done by the same node, because most shopping carts are made and reused within a day or two. Does that make sense? If, as in the illustration, you had 3 shards and you assign documents to them by date, data would eventually be stored on all the data nodes. But around December 15th, when the shopping was at its peak, nearly all the requests for data would probably go to and from a single data node, a single shard. Processing won't really be done in parallel because the data nodes managing December will get lots of requests while the other servers do little. A GUID, that's a globally unique identifier, can be generated and used as an object ID. GUIDs are long binary numbers consisting of 128 binary bits. Practically, the algorithms that generate GUIDs are very unlikely to generate the same number twice. Some have estimated that if 1 billion GUIDs were generated every second for a year, there would only be a 50% chance of a single duplicate being generated. And the generated numbers are not generated in a pattern. So if the system assigns new documents to data nodes based on their assigned GUIDs, the workload will likely be well balanced. As you can see, devising a good sharding strategy is important in achieving high performance. This is an example of one of the many performance tuning activities needed to get the most from a database management system. In a robust document store system, each sharded data subset is usually replicated one or more times. Obviously, keeping 2 or more copies of the data on different servers means that data is not lost if a single server fails. A primary shard node is in charge of adding, deleting, or changing data to ensure integrity, but read-only requests for data can be routed to secondary nodes. In a high-volume environment, a shard may need to respond to hundreds of requests per second. Even if there are 4 shards and a good sharding plan that distributes the node nicely across those data nodes, multiple requests can be sent to the same shard at the same time. Having multiple secondary replicas allows any of several different servers to respond to a request for the same document. This can reduce contention and increase throughput. Off-site replicas are also possible. For example, a primary and 3 secondary nodes may be in the same data center, ensuring that data is shared quickly between them. But updates can also be pushed out to a replica in a different location. Computers break after a while. Power sources fail from time to time. Backup systems sometimes come up short. And particular data centers can experience denial of service attacks or network overloads. While the updates to the offsite replica may be slow, meaning the data are not current with the changes from the last few seconds, this kind of built-in offsite replication can help a system recover more quickly from a disaster or a cyber attack. Did you get all that? Before we move on, consider this simplified scenario. What happens when an update comes in a millisecond before 2 separate requests for data from the same document that was involved in the update? The change might make might make it to only one of the two secondary nodes before the responses are sent back. Although the difference might be corrected in a few milliseconds, the two secondary nodes might give different answers to the same question. Monitoring and coordinating updates and requests to avoid this problem would reduce independence of the requests, and the response times would be slower because requests were no longer handled in a parallel fashion. This is a simple example of how NoSQL systems often relax burdensome control features, but may also introduce loss of functionality. Over the last several decades, billions of dollars have been spent developing the powerful generalized database platforms used for most organizational data processing. These systems are able to protect managed data from some well-understood risks. Some amazing, valuable, and useful features now come standard in relational database management systems. Foreign key constraints ensure that referenced records really exist in the database. For example, an invoice record cannot be saved with an invalid customer number, and the system can block deletion of any customers who have listed invoices. This is called referential integrity. Another example are concurrency controls, which protect from conflicting updates. If one request tries to add $100 to a bank balance while another is trying to add $200, the system forces one of the actions to wait so that the correct final answer, $300 more in the account, is there at the end. Security controls can be set to limit user access to data. So, for example, an accounting clerk might be allowed to see but not change the amount of an invoice, while a sales clerk can create an invoice but cannot post it to the general ledger. Unfortunately, each of these capabilities adds to the overhead associated with database use and slows database performance. Although the database capability landscape changes constantly, each of the features listed here has been compromised in the document store systems introduced in the last few years. We will discuss the trade-offs in future materials. For now, just realize that NoSQL systems often make things faster by compromising potentially valuable data controls. Importantly, this does not mean that NoSQL-based systems are more risky. It just means that developers may have to account for some well-known risks outside of the database management system. Okay, did you catch all that? Compared to powerful monolithic enterprise-class relational database management systems, document store systems often are installed on many relatively inexpensive computers. This allows capacity expansion to be done a bit at a time, but it means you have to allow for more frequent hardware failures. The data needed to support a particular task is stored in a single document to minimize the need for joins. Datasets are partitioned into subsets to be handled by separate data nodes. To achieve optimal performance, these subsets, called shards, need to be distributed in a way that spreads the processing load evenly across the servers. Data is replicated for each shard to protect against hardware failures and to support additional parallelization. Data integrity and security checking is often reduced in the data management system to boost performance. In many cases, these compromises are fine because controls in other parts of the system can provide adequate protection against well-known data risks. Take a moment to consider how the parallelization substrategies we covered are interdependent. In order to exploit the value of multiple inexpensive servers, datasets are partitioned across many computers. This can be good so long as requests don't require coordination of distributed bits of data. Organizing data around tasks, as in hierarchical documents, instead of by its entity type, as in relational tables, allows effective parallelization. Parallel processing is further enhanced by partitioning the dataset. Multiple servers each handle a subset of the data. Partitioning allows different parts of the system to independently respond to requests. Replication of data is also important in two ways that are closely connected to the multi-server approach. Because any one of the servers can fail at any time, backups have to be ready to pick up the load at any time. This is true for both master and data nodes. This reality means that servers have to spend computational resources monitoring each other to watch out for failure. On the good side, replication means that several computers are able to fulfill the same requests for data. That can boost total throughput. On the other hand, replication can also result in inconsistent responses. It's a trade-off. Either all requests have to be coordinated, or else two identical requests arriving at the same time might get different answers depending upon which replica responded. Did you get all that? Can you explain the difference between the hierarchical and relational representations? Can you explain how hierarchical organization supports parallel processing? If not, you might want to review the slides on joining data. Do you understand how partitioning relates to parallel processing? Partitions on multiple servers are needed to make parallelization effective. Do you understand how bad partitioning may not help at all? Review the distributing data on multiple nodes slide. Do you see how replication combined with parallel processing might result in different responses to identical requests? This illustrates potential concurrency problems related to parallel processing. This was introduced in the replication and relaxed constraint slides. Hopefully you are gaining insight into how NoSQL systems deliver value through parallelization. These insights are useful in understanding many other facets of big data management.